Okay, ladies and gentlemen, 9.5 day 2. Today we're going to add and subtract radical expressions. I do have addition and subtraction properties down here I'll go over in a second. But what we're going to do is we're going to explore these first two examples. Now, if I take the square root of 9 plus the square root of 4, what it definitely is not, it is not the square root of 13. Okay? Please don't tell me when you're adding radicals that you can ever add the numbers underneath the radicals. Not possible. What we want to do, if they're not the same, is we want to try to simplify them first. Okay, so what this actually equals, I know the square root of 9 is 3, plus I know the square root of 4 is 2, and I also know 3 plus 2 equals 5. So square root of 9 plus the square root of 4 equals 5. Okay, now in example 2, okay, square root of 5 plus the square root of 5. What that totally is not, it is absolutely not equal to the square root of 10. Please do not add numbers underneath radicals, okay? Radicals must be like each other to add and subtract. Notice the square root of 5 is the same as the square root of 5. And if radicals, number 2, if radicals are the same, you add or subtract. Whatever you do here is dictated with what's between the radicals. In this case, I'm going to add. You add or subtract the coefficients. So bottom line, what we have here is invisible 1 square root of 5 plus 1 more square root of 5. That actually equals 2 square roots of 5. Okay? We add and subtract the coefficients of like radicals in this section. Okay? Example 3, the square root of 3 plus the square root of 7. Well, I can tell you what it's not. It is not the square root of 10. Okay? So what we need to do, they have to be the same to add or subtract. Here they are not the same. So what we're going to try to do is we're going to try to simplify them each first. Well, the square root of 3, it's simplified. I have no perfect squares to take out of there. And the same with the square root of 7. There's nothing I can take out of there. So what does the square root of 3 plus the square root of 7 equal? Well, the square root of 3 plus the square root of 7, it equals the square root of 3 plus the square root of 7. There's absolutely nothing I can do with it. Okay? I can't add those numbers together. Now, the same thing holds true for any type of radical, not just square roots, cubed roots, fourth roots, fifth roots, and so on. Okay? All these three rules, they apply. I can tell you what the cubed root of 8 plus the cubed root of 27 is not. It is totally not the cubed root of 35. No, can't be that. Okay, what we need to do, if they are not the same, you try to simplify them first. So, cubed root of 8, yep, I know what cubed root of 8 is, that's 2, plus the cubed root of 27, yes, I know that one too, it's 3, and 2 plus 3, oh, this actually equals 5. Okay, so make sure you get these rules. These are, I guess I would call them Kruger-induced rules, or my own words, but get these written down in your note sheet because I'm going to erase them now, and we're going to move on here to, we're actually going to do the next 8 problems, and then we're going to go through number 14 on page 3. Okay, I was able to fit 6 on here, adding and subtracting the radicals. Now notice this one also says, assume all variables are positive, so we will not have to deal anything with any absolute values on this problem, on any of these problems again. If I take 3 square root of 7 plus 4 square root of 7, notice my square roots are the same. And because the square roots are the same, if I have 3 of them here plus 4 more of them here, well, I have 7 square roots of 7. And I'm simplified because a square root of 7 is there's no perfect squares in it. If I look at number 2, the square root of 3 and the square root of 27, they are not the same. So what I'm going to do is I'm going to get them to be the same. And I'm going to leave this negative 2 square root of 3 plus This is 3. Perfect squares in there, that's 9 times 3 to get 27. So really, I have -3 square, -2. I don't know why I changed that to a 3. I have -2 square roots of 3 plus this perfect square of a 9 is going to come out. So I have 3 times 3, so I have 9 square root of 3. And now when I double check it, now my square roots of 3 are the same. So -2 square roots of 3 plus 9 square roots of 3, that's 7 square roots of 3 for my answer there. Okay. Number 3 gets a little bit more complex only because there's variables in it. Notice, oh, I wanted my blue. Notice my roots, they're not the same. So what I'm going to try to do is my rule number 3. I'm going to try to simplify them. And here I have 2 square root 6 times y to the 4th times y minus 2y, and then I'm going to break this one up. Perfect squares in there. 24, what's my perfect square in there? That would be what? 4 times 6, right? So 4 times 6 times, I'm going to make this even, y squared times y. So what comes out is this is 2y squared, square root 6y, minus this 2 comes out with this 2 for a 4. Perfect square came out. This perfect square is going to come out. That's a y times a y gives me a y squared. Square root, I took the 4 out, not the 6, I'm sorry. 6y. So I simplified each root. And because I simplified each root, now I can see those roots are the same. So if I have 2y squared, square roots of 6y minus 4y squared. Now because the variables in there, for these to be like terms, all the variables and the root needs to be the same. So this is going to give me -2y squared square root 6y. Okay. When I come back here, excuse me, to number 4, check it out. My roots are the same. Because they're the same, -9 plus 10, well, that gives me square root 15x. You can put the 1 out front if you want, because there's only going to be one of them. You do not have to. And notice there are no perfect squares in 15. So that would be my final answer on that one. Number 5, square root of 8, square root of 18. They're not the same. I need to get them the same. So when I'm looking for perfect squares, I see this is technically 11. 4 times 2 gives me my 8, minus 3. 9 times 2 gives me my 18. So this is really, this 2 comes out. So this is really 22 square roots 2 minus, this 3 comes out, multiplies with that, so that gives me 9 square roots of 2. Now I can see my roots are the same. If I have 22 of them in the beginning and I take 9 of them away, well then I have what? 13 square roots of 2 for my final answer. Okay. Last one, number 6. It doesn't matter how many roots there are. Makes no difference. When I'm looking at my roots, check it out. None of them are the same, so I can't add any of them together. So I'm going to try to simplify all of them. Okay. So this is going to be 2, 4 times 2 minus 5, 4 times 3 plus 7, and that's just a square root of 2. There's nothing I can do with that one. So I know this perfect square root of 4 is out, so it's 2. So this is 4 square root 2. This 2 comes out, minus 10, but this one's a square root of 3 plus 7 square roots of 2. Now, I only have 2 roots in this case that are the same. I have 4 square roots of 2 plus 7 square roots of 2. Well, that gives me 11 square roots of 2 minus 10 square roots of 3. And because these 2 roots are different, I can never put them together. I can't add them, can't do anything with the numbers. So I stop and I circle that one, and I am done with that one. Okay, I'm going to let you work on the next few, and I'm going to get locked and loaded here again. The last two examples on this page before we put multiplication and addition and subtraction together. Again, I cannot combine these two because these radicals are different. So I need to simplify each radical first. Okay, so this is really 3 times, I'm going to call that x to the 8th times an x minus x to the 4th. 27 is 9 times 3 times x in there yet. Okay, there's no perfect squares in 3, but the square root of x to the 8th power, that's x to the 4th. So I have 3x to the 4th, perfect square there. And that leaves me with a 3x underneath minus perfect square of 9 comes out, so that's 3x to the 4th. And the 3 and the x stay underneath. Okay, so then right out of the blocks I can see now I got to hitch that whole, because there's a variable on the outside, it takes all the variables and the root to be the same in order to add those numbers in front. And if I have 3 of these here minus 3 of these here, I guess I don't have any left. And when I look at number 18, well, I'm going to look. Hey, check it out, number 18, there's 4 of them. It looks super complicated. But notice that one, and that one are all the same. So I can put those 3 together quick. So I really have 2 minus 1 plus 3. Well, that gives me 4 cube roots of 16 minus 2 cube roots of 24. Well, now check it out. Those are not the same, but I also know they're not simplified. And now I'm looking for perfect cubes, not squares. So I'm looking for perfect cubes. So that's 4 cubed root. That would be 8 times 2 minus 2 cube root. That's 8 times 3. So if I rewrite these, this perfect cube of 8 comes out, which is 2. So this is 8 cube roots of 2 minus this cube root of 2, or cube root of 8 comes out, it's a 2, 4, and that gives me a cubed root of 3. Notice these cube roots here, they're simplified. They're different, so I can't put them together. So that is my final answer on example 8. Okay, here on the next page, top of page 3, we're going to combine addition and subtraction with multiplication. Just remember your order of operations. You must multiply before you add or subtract. So this is 2 square roots of 5 times the quantity square root of 6 plus 2. Well, I got to distribute first. Well, notice there's an invisible 1 in here. 2 times 1 is 2. The square root of 5 times the square root of 6 gives me the square root of 30. And then I need to distribute here. And this is like times the square root of 1. 2 times the square root of 1. So this gives me plus 4 square root of 5. Okay? Now I just need to see, can I break this down? Well, are there any perfect squares in 30? And the answer to that question is no, and I can see it if I prime factorize it. It's 2 times 15, which gives me 3 times 5. Notice none of these prime factors of 30, there's not multiples of any of them, means there's no perfect squares in there. And these roots are not the same, which means that's my answer. I cannot put them together. Number 2. 2 terms times 2 terms. Oh, did I miss a sign in there? I did. There's supposed to be a plus right in here. Plus square root 5. Sorry about that. So there is 2 terms times 2 terms. And how do we deal with that? Well, you can think of double distribute or the acronym FOIL. So I distribute 2 to the first one. 2 times 3 is 6. Distribute 2 to the second one. 2 times the square root of 5 is positive 2 square root 5. Then I need to distribute here, square root of 5 times 3. Well, that's plus 3 times the square root of 5. Square root of 5 times the square root of 5, well, that's a square root of 25, but a root times the exact same root is the number underneath with no root, because 5 times 5 is 25, square root of 25 is 5. Then I look, oh, check it out, like terms, 6 plus 5, those are 11. Square root of 5 and a square, oh, those square roots are the same. If I got 2 of them here plus 3 of them here, that's plus 5 square roots of 5. I can't add these together because this one doesn't have square roots of 5 with it. Final answer. Number 11, I'm going to distribute again. Now I'm distributing square root of 3 times this quantity. Well, first thing I'm going to do is I'm going to take that. Well, there's a 1 in front of here. So 1 times negative 5 is negative 5. Square root of 3 times the square root of 10 is square root 30 plus the square root of 3 times the square root of 6 gives me the square root of 18. Notice these are different. I need to see if I can get them the same. Well, square root of 30 I knew back here from this example had no perfect squares in it, but this one does, so that means I need to extract it first. So this is really negative 5 square root 30 plus 9 times 2, because there's my perfect square of 9, 5 square root 30 plus 3 square root 2. They're still obviously not the same, but you need to make sure you simplify every radical in the whole expression and then put together the ones you can. And I cannot put them together because they're different. So that is my final answer. And I will get the last 3 problems up on the board. Hopefully you try them before I go over them. Okay, number 12. Because there's an addition symbol in here, I can't just distribute that squared in here and call this 7x plus 9. Because I'm squaring a quantity of 2 terms or more, 2 or more terms, I really have the square root of 7x plus 3 times, remember what it means to square something, times itself. So that I have to double distribute here. The square root of 7x times the square root of 7x is 7x. The square root of 7x times 3 plus 3 square root 7x. 3 times the square root of 7x is 3 square root 7x. 3 times 3 plus 9. Remember, when you take 2 terms, type 2 term, you should always get 4 terms, and then try to collect like terms. Well, 7x and 9, they're not like each other, but a square root 7x and a square root 7x, they are like each other. So this 7x stays by itself, plus, well, if I have 3 of these plus 3 more of those, I have 6 of them, plus 9. And I would always want to write it in descending order, and I can't combine anything else. So I would put my biggest power first, down to my next power, all the way down to my constant. Okay? Number 13. 13 is a major, major topic. Big idea. Conjugate pairs. We talked about multiplying conjugate pairs with imaginary numbers when we had to get rid of an I in the denominator of a fraction or something. A huge topic that's going to come into play tomorrow again here, excuse me, when we divide. But in the end, I still have 2 terms times 2 terms today. So I'm going to double distribute again. So 7 times 7, it's 49. 7 times negative root 3 minus 7 square root 3. 7 times 1, and then square root of 1 times square root of 3 and square root of 3. Then I got to distribute my square root of 3. It gives me plus 7 root 3. The square root of 3, positive square root of 3, times negative square root of 3 gives me negative 3. And whenever you multiply, huge idea, guys, really important for many topics in math, conjugate pairs, when you multiply conjugate pairs, in the end, you're going to usually end up with 1 term half the time in the end, okay? As I know, here's that one and that one. negative square root of 3 plus positive square root of 3, well, they kind of wipe each other out. And 49 minus 3, that gives me what? 46. So that one just simplifies to a number. Okay? Again, here, conjugate pairs again. Remember, conjugate pairs. 2 terms times 2 terms. Everything about first term's the same, second term's the same, last term's the same, last term's the same. The only difference is the sign between them. When you multiply conjugate pairs, magic happens. Let's do the old double distribute here again. 4 times 4, 16. 4 times square root of 5 plus 4 root 5. Negative root 5 times 4 minus 4 root 5. Negative root 5 times positive root 5, negative 5, combine like terms, 16 minus 5, that's 11. Positive 4 root 5 minus 4 root 5, they wipe each other out, and I just get a number in the end. Okay? Big topic. We will be coming back to number 13 and 14 tomorrow as a big idea.